So we've been looking at open systems now, trying to understand how we conserve energy in systems where mass can flow into and out of our control volume. I've been making the argument that for these types of problems, first, we want to figure out where we draw our control volume. Then, we need to figure out what happens to the mass. And finally, we try to figure out what happens to the energy. In last class, we were introduced to the first law for these open systems. And today, in lecture 16, we're going to go through an example problem where we're going to use a first law analysis on an open system like this. But before we do that, we will do a bit of a review of what we learned last class. So last class, we were introduced to this open version of conservation of energy, or the first law of thermodynamics, using open systems. So we know that we have a term here that talks about how much energy is being stored or depleted from our control volume. We have the rate of heat coming into the system, the work being performed by fan blades that are inside our system, and then we have these terms that tell us about the amount of energy that's coming in with our mass and going out with our mass. We remember that if kinetic energy and potential energy terms stick around, units are going to be difficult. This is going to happen if it's metric, where typically we would divide both of these terms by 1,000, and it's even worse if it's imperial. Right? So the units here for the kinetic and the potential energy terms are always going to be important, even when you're dealing with the metric system. If we're dealing with the imperial system, our equation changes a little bit, right? Because we have this thing where 1 pound mass has a weight of 1 pound here on Earth, we have to divide by GC, which is sort of the gravitational energy here on Earth. But remember, it's got some funny units. So even after we do this, we'll probably end up having to convert this from something like foot-pounds per pound mass to BTU per pound mass, because that's the unit that we'll look up enthalpy for in the textbook. So units are always a pain for these two terms. I mean, most of the time we're not going to be worried about these terms, but it does matter in things like jet engines what the velocity of the fluid is. So if these terms stick around, we have to be aware that we're going to have to do some unit conversion. So what else did we learn last class, right? So hopefully you've known this the whole time, but thermodynamics is awesome, right? The first law, it gives us a lot of power to do different things. And as engineers, right, if we can understand how each one of these processes is kind of like a Lego block, then we can put things together in really cool ways to make things that are interesting, right? So engineering is not just about knowing how to do math and physics. It's really about being creative and using our understanding of the physical world to try to get creative solutions that solve problems in society, right? And what we're going to learn here in thermodynamics is that each one of these processes is like a Lego block, and we're going to put them together in ways that end up being very cool. Right? So we go from the Lego block over here to the Millennium Falcon. We talked about how in a case of a power plant, like if it's a coal-fired power plant or a nuclear power plant, we can actually look at that power plant as a sum of all its different components. And in this case, all of these components, the pump, the boiler, the turbine, the condenser, they're all individual open systems. So there's a process that happens in each one of these components. And if we understand that, then we can put the components together to make something that looks like a power plant. And we'll learn in this class maybe what a basic power plant looks like, but then we'll learn how to add more blocks so we can do things like improve efficiency, which means that for the same amount of energy, we're burning less coal. So our building blocks, unfortunately, in this class are not pieces of Lego, right? Which would be super fun to do, but instead, we have these mechanical components. So things like turbines and pumps, throttling valves, we'll use nozzles and diffusers, right? So that's here you either get a reduction in area, which increases the speed of your flow, or you get an increase in area, which slows your flow down. And then we have heat exchangers, where we typically have two streams of fluid and we're trying to exchange heat between them. Often, like showed in this shell and tube heat exchanger, we don't want to mix these fluids up because maybe they're different types of fluid, like, for example, engine oil and water. So we're going to put these things together to understand how power plants work, how automobile engines work, how jet engines work, and how air conditioners work. We do that by looking at each individual components, right? And each of these components will be open system components. So first, we have to look at each individual component, which is the skill we're trying to learn now. We conserve mass as it moves through our component, because these are open systems. That lets us then begin to conserve energy. Oftentimes, we'll assume that each one of these components is a simple system, which means that either the purpose of the system is to transfer heat, or the purpose of the system is to put work into the system or get work out of the system. And then we'll use the first law to find the power or the rate of heat transfer in the process that goes on in each one of these components. Another thing we learned is that turbines and pumps end up looking very similar when we do the first law. So again, I'm always going to encourage you to start with the first law. Start from first principles, and then we'll make some assumptions to cancel out different pieces of information, and we'll be left with an equation for the different type of process. And that's good because then we can get something like power is equal to mass flow rate times H in minus H out. Now, it's a little bit different. The way that I teach this is a little bit different than what our textbook says, because I'm always going to preserve this idea of hip to win, this sign convention we have where work in is negative and work out is positive. So you'll get positive work or power from a turbine, but negative work or power from a pump. If you go from the first law, you will always get that power or work is high ho, right? H in minus H out. And I remember that because I know from watching lots and lots of Disney movies that the dwarves work really, really hard, right? So if I'm trying to find work, I remember the song that they sing, right? It's high ho, so H in minus H out. But I can always get here just from first principles, starting with the first law, right? And this, if I trust the sign convention, I'll get the right answer every time. And I won't have to do, kind of the process that the textbook does where you kind of have to remember what cycle you're working on. Sometimes things are positive. Sometimes you subtract them. Sometimes you add them. It's not just an absolute value. We just put it into the first law. We trust the sign convention and we remember what the sign convention means. And in this case, work in is negative. That's from a pump or from a compressor. And work out is positive. That's what we get from a turbine. So now I want to show you how we do an example for conservation of energy. Now this example you may remember because we did this same example for conservation of mass. If you remember, we had 100% of the mass flow rate coming in at the inlet, 20% of the mass flow rate going out at the outlet 2, and that means that from conservation of mass, the rest, the 80% of that mass, went out at outlet 3. So we did conservation of mass on this problem already, but now we're asked to find the work generated or the power generated by the turbine. And we want to comment on the magnitude of the terms in the first law. So that means we got to try to make some assumptions about what's going on. Here, the problem tells us to assume steady state flow, to assume that the velocities are approximately equal in 1 and 3, although we found the velocities already. We're going to assume that there's constant properties at each one of these inlets and outlets. So what this means when we assume constant properties, we mean that all the fluid that's coming in here at state 1 has a particular pressure and temperature and volumetric flow rate. So this is like we're taking the average velocity here, the average temperature, and the average pressure. And that would be true not just at the inlet, but at the two outlets. So here we're going to start with our conservation of energy or our first law equation. We're going to assume that the system is at steady state. So that means that over time, there's no storing or depleting of energy inside our control volume. We're going to assume that this is adiabatic. Now, for many, many systems, when we do these open system analysis, we'll assume that they're simple systems. Now, to do that, we need to understand what the purpose of the component is. So now remember, the purpose of the component for the turbine is to produce power. So if we're trying to produce power here, we shouldn't cancel out power. So for these open systems that are trying to either produce or consume power, we'll typically assume that they're adiabatic unless we have some information, enough information to find the heat transfer. Really, I guess what we're saying is not necessarily that this is adiabatic, although that's kind of the strict interpretation of this assumption. Another way to look at this is just that we're assuming that the heat loss from the turbine is much less than the power generated. So it might not actually be zero. It's just very small compared to the power that we're generating. We'll assume that the change in elevation between these ports, even though it exists, we'll assume that it's small enough that we don't need to think about it. So if we do that, now we have three different, we have one inlet and two outlets, right? So what I did between here, I said, okay, for inlet 1, I have the mass flow rate in times H1 times V1 squared over 2. And for the exits, we have the mass flow rate out times H out, V out squared over 2. But we're going to do that both at state 2 and at state 3. So when I do that, I get this equation. So now what do? I want to take stock of the variables. Do I know what they are or do I not know what they are, right? Because that'll help me understand if I'm ready to solve the problem. Because ultimately, I want to get to a point where I have the same number of equations as unknowns. So I don't know the power. I do know the mass flow rate at 1, because remember we solved that before. I don't know H1 because I haven't fixed the state yet. I know V1 here, so I assumed V1 was equal to V3. When I was talking before, we know V2 and V3 because we solved those already, but we didn't know V1. So we made that assumption, okay, we're going to assume that V1 is equal to V3 because we didn't know what V1 was in the original problem. I do know mass flow rate 2 because I figured that out. Remember, 20% of the inlet mass flow rate. I don't know H2 because I haven't fixed the state. I found V2 when I did the conservation of mass. I do know m dot 3, right? Because if 20% of the mass comes out at mass flow rate 2 and we're at steady state, that means that 80% of mass, the rest of the mass flow rate, must come out at state 3. I don't know H3, but I do know V3. So here, I'm at the point, this is not a bad point to be in thermodynamics, where I have the equation, the thing that I'm trying to figure out, I don't know. But then the other things that I don't know are things that I can figure out by fixing the state, right? So we need some state information here. So we go back to the state table that we had for the first part of the problem when we were doing conservation of mass. Remember, we put the mass flow rates in here. We put the velocities in here, and I've assumed that the velocity at 1 is equal to the velocity at 3. And now we want to check out what the enthalpies are, the specific enthalpies. So this is a table that you might find in an FE handbook. So here, what we know about state 1 is we have a pressure and we have a temperature, right? So I think we've already found specific volume here. So we know that this is a superheated vapor. So we can check that out. So this is a table for 1 megapascal. Remember that if we want to go from bar, which is 100 kilopascals, to megapascals, we have to divide bar by 10. So 10 bar is equal to 1 megapascal. Here I know the temperature is 500, so I can just read the enthalpy off here, the specific enthalpy. So it's 3,478.5. So I put that into my table. Now I want to figure out what's going on at state 2. So here I know that the temperature or the pressure is 8 bar, right? So 0.8 megapascals. And the temperature is 400 degrees Celsius, right? So it's nice. We don't have to interpolate because this is a row that's right on our table. So now I know we have been used to in closed systems looking up specific internal energy. But remember, enthalpy is specific internal energy plus pressure times the specific volume. So the enthalpy will always be higher than the specific internal energy. Here, the specific enthalpy is 3267.1. So I put that into my table as well. Now, I want to find state 3. So state 3, it tells me that there's some quality. That means that it's a two-phase mixture, right? It's some mixture of saturated vapor and saturated liquid. And here, in this case, I have 90% saturated vapor, so I should be close to the Hg value, right? So here I got to find on my table the row that's 90 degrees Celsius. So that's here. And I know that I'm going to be somewhere between HF and Hg, right? Closer to Hg though, because this is for the saturated vapor and I have 90% saturated vapor and only 10% saturated liquid. So here I remember my equation for quality, that H3 as a function of quality is HF plus the quality times HFG. Remember, HFG is Hg minus HF, so I could figure that out if I wanted to. But here the table already gives me the subtraction, right? So if I use HFG, it's one less thing that I could mess up when I'm putting it into my calculator. So here I get that the enthalpy, the specific enthalpy here is 2,431.8 kilojoules per kilogram. I look at that, I feel like it makes sense because it's much closer to 2660 than to 377. So this seems to make sense, and the units are right, so that's good. I didn't mess up the units. So now I put this in, and this makes sense too, because here the highest energy fluid comes in at state 1, right? Because the purpose of the turbine is to take some of that enthalpy that's wrapped up in my fluid that's coming in and turn it into mechanical work, right? Turn it into this shaft that's spinning, right? Because we're letting this steam expand over the fan blades inside the turbine, right? So we're trying to get this to spin, and that means that the energy that's stored in the fluid in enthalpy has to go down, and that's what we're seeing here. So now I go back to the equation that I had from the first law about power generated by the turbine, and I put all this in, right? So I can look at values in each one of these terms. So first I'm going to look at the first term, right? So now I have the mass flow rate at 1 multiplied by H1 plus V1 squared over 2. So I know the mass flow rate. H1 I looked up. And now I look at this velocity term, right? Now maybe, right, because I've been talking about this, maybe your spidey sense is already tingling, right? Maybe you understand that this is probably not going to be the right unit. But let's carry the equation through, right? So here I get 38,581 kilojoules per second. That's going to be this times this, right? Here, so this is nice, right? Because I'm trying to find power, right? So a kilojoule per second is a kilowatt. So that's good. This is what I'm expecting. But over here, I got 635.4 kilogram meter squared per seconds cubed. I don't necessarily know what that is, right? So I got to think a little bit, right? So I can use Newton's first law to turn the kilograms into newtons, and then eventually I'm going to get Newton meters per second, right? Because this is, if I think about this, I know from Newton's second law that force equals mass times acceleration. So here's a mass. There's an acceleration in here, right? It's going to be mass or meters per second squared. So then if I take that out, this would be kilogram meters per second times meters. So Newton meters per second. So then I get joules per second. But I can't just add kilojoules per second to joules per second. I got to divide this by 1,000. So I want you to notice something here, right? Now, we'll see this as we go through, but a lot of times we'll end up neglecting the change in kinetic energy. And maybe you can see why from this term, or you can start to see why from this term. So from the enthalpy in this term, right, we get 38,581 kilojoules per second. From the kinetic energy, I get 0.635 kilojoules per second. This number is much, much bigger than this one, right? So maybe, and we'll try it both ways, but maybe if I didn't even have this term in here, if I neglected this term, if I said the kinetic energy wasn't important, I would get essentially the same answer, right? So this is 0.001% of the total power here at state 1. Now, let's see what happens in the next term, right? This should be m.2 up here, or 0.2 m.1 if you prefer. So let's figure out the second term here. So again, I know the mass flow rate. I looked up H. I know velocity at 2. This is the same calculation that we had before. We'll get different numbers, but we still have the wrong units here in the kinetic energy term. This will basically always be the case, right? So this is really joules per second. We're going to divide by 1,000, and we're going to get kilojoules per second. So again, we're dominated here by the enthalpy term, and the kinetic energy term is very, very small, 0.004% of the total power here at state 2. Let's do the same thing for state 3. Again, conceptually, this is the same, even though it's different numbers, right? If I work this out, you always got to carry your units in your calculations, because otherwise you'll end up adding kilojoules per second to joules per second over here. But you might not even know this is joules per second if you do this too quickly, right? So this is joules per second. And again, the kinetic energy part is a very, very small part of the total here at part 3. So I get that the power generated by this turbine is 9,750.2 kilojoules per second, or kilowatts. Right? So that's the same number in kilowatts. If I wanted to convert this to megawatts, right, then this is the beauty of the metric system. To go from kilowatts to megawatts, all I do is divide by 1,000. So this is 9.75 megawatts. So now, a lot of times when we deal with turbines, we're going to make the assumption that the change in the kinetic energy doesn't matter. So even though from our conservation of mass equations, we found out the velocities at state 1, state 2, and state 3, what if we just said from the outset, because now we've seen that they didn't really make too much of a difference in each one of those individual terms. So what if we said that the change in kinetic energy was not important in a problem like this? Right? Now, I would just get the terms if I didn't have the kinetic energy terms. And remember, those kinetic energy terms were always like, 0.00 something percent of each total, right? So here, again, if I do this, I also get 9,750-ish kilowatts, right? So my agreement with my solution with and without the kinetic energy is, 0.002%. So these two models, with and without kinetic energy, tell me the same thing, right? Now, this is going to be true for lots of the components that we're going to talk about. It's going to be true for turbines. It's going to be true for pumps. It's going to be true for heat exchangers. It's not going to be true when we talk about diffusers and nozzles, because the purpose of diffusers and nozzles is to change between enthalpy and kinetic energy. So you'll see on a jet engine, right? So right at the front of a jet engine, you have a diffuser, because you're trying to take the kinetic energy coming into the jet engine and turn that into more enthalpy. And then at the back of a jet engine, the purpose of a jet engine, we're trying to maximize the velocity of the fluid coming out of the back of the engine. So there we have a nozzle where we're going to try to constrict the flow to try to maximize the velocity of the fluid that's coming out the back of the engine. But we'll get to that later on in the course. Hopefully, from this example, you've seen a couple of things. So first, how do we take the first law after we've done conservation of mass in an open system, and how do we use the first law, manipulate it with different assumptions, get to an equation, and then put information into that equation so we can find the power in this case. But then hopefully after that, you also see how some of these assumptions actually are pretty reasonable, right? So here the change in kinetic energy tended not to be very important, even though we knew the velocities here. Just because you know the information doesn't necessarily mean you have to put it in. If we did the same thing for gravitational potential energy, you also would have seen that it's extremely small compared to the changes in enthalpy that we see in these types of systems. So this is a turbine. Over the next couple classes, we'll go through different examples for different components. So thanks very much, and I'll see you next time on Thermodynamics.